Hello, this is Dr. Baxley. Welcome to the second part of Chapter 6 Thermochemistry lecture video series. In this video, the topics of state functions and enthalpy will be introduced. It's important to note that the absolute energy of a system can't be measured. Instead, we have to measure the changes in energy, or the energy difference between an initial and final state. Because energy can only be measured in its initial and final states, energy is considered something called a state function. A state function depends only on the difference of initial and final states of the system. The other kind of system is a path function. The path function depends on the path taken. Here's an illustration to show the difference between a state function and a path function. Here's a picture of Bishop Peak. One can think about going up Bishop Peak, starting at the parking lot on Patricia Drive, and then getting up to the top of the mountain while hiking. In terms of the altitude going up the mountain, the altitude only depends on the initial spot where you start hiking and the top of the mountain. The altitude doesn't really depend on the path you take. If you take a different path to the top of the mountain, the altitude difference is the same. Therefore, the change in altitude up a mountain is a state function. However, if one thinks about the distance traveling up the mountain, the distance between the two paths that are shown is going to be different. So traveling up a mountain is a path function. Here's another example to show the difference between a state function and a path function. One can take a battery, like a D cell or a C cell, and connect a wire to it. If one does that, top to bottom or positive to negative, the wire will get really hot and the battery will eventually short circuit. One can do the same kind of thing by putting a fan in between the two ends of the wire. As the battery discharges and electrons move from one side to the other, the fan motor will spin a blade and push some air around. In both cases, we could look at the energy of the charged battery versus the energy of the discharged battery, and how much energy is lost from going from charged to discharged. In the short circuit side, all that happens is that the wire gets really hot as the charged battery goes to discharged. However, for the fan version, there's some heat that's generated, for sure, in the wire and the fan motor, but there's also some work being done as air is being blown as it hits the fan blades. So is change in energy a state function or a path function? If you look at the energy levels, it doesn't really depend on the path the energy takes, whether it's all heat or some heat and work. And so change in energy is a state function. Now we're going to talk about enthalpy. Enthalpy is the amount of heat energy that a substance has. However, just like raw energy, one can't measure the absolute enthalpy of a system. So what chemists do is they measure changes in enthalpy. The triangle here is used as the symbol for change, or delta. Is delta H a state function then, or a path function? Because delta H only applies to final minus initial, the delta H must be a state function. In terms of enthalpy, enthalpy is always a focus of the system. For chemistry, that's the chemicals. So delta H always has a positive value if the chemicals in a system, the reactants, gain heat from their surroundings. Delta H will have a negative sign when the system, the chemicals or the reactants or the stuff in the beaker, when the reactants lose heat to the surroundings. Most chemical reactions that occur spontaneously or naturally are in the negative delta H column. Reactants that absorb heat energy from the surroundings are given a special name. Those are called endothermic reactions. When reactants transfer or release heat energy to the surroundings, those are called exothermic. Kind of like because the heat is exiting the reactants. Endothermic reactions, if you had a container with an endothermic reaction in it, it would feel cold. An exothermic reaction would feel hot. You might have seen some of these reactions in day-to-day life. We've all seen exothermic reactions with fire or flames, but you might have had a sprained ankle or a bruise and had an instant cold pack applied to your wrist or your ankle, maybe on the soccer pitch. Those instant cold packs are endothermic reactions. As soon as they start, by mixing up the chemicals in the bag, the chemicals start absorbing heat energy from the surroundings, and they feel cold to you. Here's just a concept check. If heat energy is going into the system, is that a positive delta H or a negative delta H? And is that endo or exothermic? When heat energy goes into the system from the surroundings, that is a positive delta H, and that is endothermic. The next concept should be pretty easy then. If you look at the heat leaving the system to the surroundings, that has to have a negative sign for delta H, and that is exothermic. Why are some reactions exothermic and some endothermic? I'd like you to complete this picture. I'm going to put the reactants here just midway up in terms of potential energy on the y-axis. The x-axis has reactants going to products. So products are going to be over here somewhere. But I'd like you to figure out where to place them. In terms of an exothermic reaction, should the products be way down here, or should the products be way up here compared to the reactants? So take a moment, pause the video, and figure out where on that graph you think the product should be. Okay, ready to find out? In an exothermic reaction, the reactants are releasing some energy to the surroundings. That means the products have to be lower in potential energy. That energy was given off as heat to the surroundings. As you read through chapter 6, even with the help of the reading guide, you're going to find that it has lots and lots of letters in it and turns into what I call alphabet soup. You're going to find Q, and you're going to find U, and W, and P, and V, and E, and of course H, along with T for temperature. It really does turn into a can of alphabet soup. But for chemists, the most important part of the middle of chapter 6 is the relationship that delta H, or the change in enthalpy, is equal to the heat energy change, or Q, divided by the number of moles of the reactants, or number of moles of reaction that are taking place. Remember, the change in enthalpy is the heat gained or lost for a chemical reaction. Q can be calculated by multiplying the mass of a substance that's changing temperature by how much it changes temperature, the delta T, by the specific heat capacity of that particular substance. This is the end of part 2 for the chapter 6 lecture video. In part 3, you'll learn a lot more about this topic, specific heat capacity.